Okay, kids, it's time for the next video lecture, this time on angular momentum. Angular momentum is the analog for rotational motion to linear momentum. Linear momentum, if you recall, was a product of an object's mass and velocity. For rotational motion, the angular momentum is a product of the moment of inertia and the angular speed. In this situation, the moment of inertia is acting as the mass, just like it did in the previous formula we looked at, where the net torque was equal to the moment of inertia times the angular acceleration. And of course, instead of linear velocity, here we have an angular speed. We're going to be using all of the quantities you see here to solve problems involving angular momentum, just like we use mass and velocity to solve for problems involving linear momentum. One of the things that you should remember from the unit on momentum is that we talked about collisions. In the collisions, we had momentum conserved both before and after the collision. The same thing is true for angular momentum so long as we don't have a net torque applied to the system. We can apply this to real-world situations in which we have an object in rotational motion. So let's say we have a figure skater, and the figure skater brings their arms in closer to their body. This will always increase the skater's angular speed. Now, why is this the case? Think about the quantities that go into determining an object's angular momentum, answer the question, and then move on. The reason why bringing your arms closer to your body as you spin increases your angular speed is because one is decreasing their rotational inertia. You're bringing more of your mass closer to your center of rotation. So, assuming that your overall level of angular momentum is going to be the same both before and after you bring your arms in closer to your body, if you decrease your moment of inertia, then your angular speed must increase to compensate. This general principle can be summed up with this formula. The final angular momentum for a system equals the initial angular momentum of a system, so long as all we're doing is, say, moving around the radius of rotation or where the mass is distributed. If we apply a torque to a system, then obviously we can change the angular momentum by accelerating the object. So here's a problem involving that very concept, where what we're going to be doing is simply changing the radius of rotation for a yo-yo. So I give you enough information in the beginning of the problem to calculate the angular speed for the yo-yo. All right? I even give you the angular momentum in the third line if you look closely. Then what I want you to do is recalculate what the angular speed would be if we're going to double the radius from 1 meter to 2 meters. Go ahead and try to solve this yourself, and then move on when you're ready. So when we enter our information into the formula for angular momentum, we get an angular speed for the yo-yo of 12 radians per second. After we double the radius, we notice that the angular speed drops to 1/4 of the value, or 3 radians per second. This is exactly what we should expect mathematically. If you look at the effect of doubling the radius, since we square the radius to determine the moment of inertia, what we're doing by doubling the radius is increasing the moment of inertia by a factor of 4. Therefore, to keep everything the same, we increase the moment of inertia by a factor of 4 on the right-hand side of the equation. The angular speed must drop by a factor of 4 for us to keep our angular momentum the same value. Most of the problems that you're going to be having in this class that will involve the conservation of angular momentum will be very similar. The distribution of mass on the object will change, or the radius of rotation for an object will change, and you'll have to recalculate the angular speed or some other quantity as a result.